This is the second video on chapter 37, and there will be one more. So I'm not going to do any examples in this video. I'm simply going to explain what a differential is. And so the title of this chapter is Linear Approximations and Differentials. In the first video, I showed you what a linear approximation is and did an example. In this video, I'm going to explain differentials, and in the next video, I will do an example or two. Now, as a general rule, linear approximations are used to approximate function values. Differentials are used to approximate changes in function values. They can be used interchangeably. If you can approximate a function value, you can approximate a change, and if you can approximate a change, you can approximate a function value. But as a general rule, the algebra usually works out a little bit simpler if you use a linear approximation to approximate a function value, and you use a differential to approximate a change in a function value. And so this is our setup. I'm just going to explain definitions 297 and 298. We start with a function. Y is f of x. Delta x is going to represent a change in the variable x. So your variable x is going to change from x to x plus delta x. Delta x does not have to be positive, it can be negative. So the x plus delta x could be, the delta x can be a negative change. So x plus delta x might be less than x, and it might be more than x. So just keep in mind delta x is allowed to be negative. Now, with that change in x comes a corresponding change in y that we call delta y. As x changes from x to x plus delta x, then what happens to y? It changes from f of x to f of x plus delta x. And so this difference is the change. So again, x changes from x to x plus delta x. The y variable changes from f of x to f of x plus delta x. So we subtract these two to get the difference. Now, what happens if you take the limit as delta x goes to 0 of delta y divided by delta x? Well, what is delta y divided by delta x? It's f of x plus delta x minus f of x divided by delta x. You take the limit as delta x goes to 0 of this, what do you have? You have the derivative of f. In the definition, we usually call this delta x h, but it doesn't matter what you call your variable. If you take the limit as h goes to 0 of f of x plus h minus f of x divided by h, we just rename our h delta x, and we have the exact same thing, just written differently. So this is the derivative. Now, this limit is this derivative. That means as delta x is close to 0, if delta x is close to 0, then delta y divided by delta x is close to f prime of x. And so that's why we have here delta y divided by delta x is approximately, oops, this should be f prime of x, that should be f prime of x. That was wrong. Okay, so delta y divided by delta x is approximately f prime of x. Delta y is approximately f prime of x times delta x. So that's what these changes are. Delta x, change in x, delta y is a change in y. This is what we're interested in. We want to know what delta y is. But we're going to use what we call differentials to approximate delta y. So we're going to introduce two new variables. dx is going to be our independent variable. dy is going to be our dependent variable. dx, independent variable, means it can take on any value that we want. So what we're going to want is for it to be delta x. We're going to choose dx to be delta x. It's the independent variable. We can make it anything we want, and this is what we want. Then we define dy to be f prime of x times dx. This is how we define dy. Now, what do we have with this f prime of x dx? Okay, this is what we call, first of all, this is what we call our differentials. Our differentials are the dx and the dy. These are our differentials. Why are we interested in them? forgetting my prime. Okay, we're interested in those because delta y is approximately f prime of x times delta x. And we're going to set dx to be delta x. So delta y is approximately f prime of x delta x, which is exactly equal to f prime of x dx, because that's how we made it. We set dx to be delta x. dy is defined to be f prime of x dx. So this f prime of x dx is dy. What that means is that delta y is approximately equal to dy. Why do we do this? Same reason we use the linearizations. As a general rule, the dy, which is f prime of x dx, is easy to calculate. The delta y is more difficult to calculate. And so what we're going to do is we're willing to trade accuracy for ease. So dy is fairly easy to calculate, and it's approximately the delta y that we're interested in. So rather than calculating delta y, we calculate dy, and we say those two things are approximately equal.